Okay, so the association is just a relationship between variables. Correlation is very often misused. It's a numerical measure of the strength of a linear association of quantitative variables. Okay, a lot of times you'll see reports and they'll talk about the correlation between eye color and GPA. You can't have a correlation between a categorical variable and a quantitative variable. Okay, the relationship also must be linear in order to use correlation. So that means it has to be in a line. Okay, it can't be curved or it can't be curved. So correlation is very frequently misused for association. Association and correlation are interchanged out in the real world, but statistically, correlation only applies when they're quantitative variables that are linearly related, and it's a numerical measure. The explanatory variable is the x variable. And place it on the x-axis of the graph. We use it to account for, explain, or predict the y variable. The response variable is the y variable. It's placed on the y-axis, and it responds to the x variable. Okay. If your x variable is time, right, and your y variable could be home prices, right? Over time, home prices have increased. Those are both numerical measures. And so we can talk about correlation on those. Correlation specifically, the letter R is used for correlation. It's the numerical measure. The sign gives the direction. So if it's a positive, the relationship is positive, meaning it's increasing from left to right. If the sign is negative, that means it's decreasing from left to right. So the sign does not tell us how strong the relationship is. It just tells us what direction the relationship is. Correlation must always be between -1 and +1. You cannot have a correlation of 2. You cannot have a correlation of 1.1. Correlation is always between -1 and 1. A correlation of 1 or -1 means the data falls in a perfectly straight line, has a linear relationship like you learned in algebra, y equals mx plus b. A correlation of 0, let's add this. Is no relationship. It means the points are just all this big cloud and there's really no pattern. So the farther away from 0, between 0 and 1, the stronger the relationship. X and Y are treated symmetrically. So if you switch the axes, your correlation doesn't change. There's no units. Okay, we don't use units when we talk about correlation. It's not affected by changes in scale or center. So if I change it from feet to inches, the correlation doesn't change. If we change it from dollars to pounds, the correlation doesn't change. It's the strength of a linear relationship only. And it's possible for variables to have a strong association, but a small correlation if they are not linear. Data that is parabolic, if you see data that looks like this, in a very strong, tight parabola, this has a correlation near 0, but it has a strong association. There's a strong relationship between those two variables. It's just not linear, which is why you can't use correlation to describe it. Describing a scatter plot has 4 things we talked about, just like we had 4 things to talk about a distribution. On the test, a lot of you talked about all kinds of things when you were comparing the box plots, but you didn't talk about the shape, the center, and the spread, which are the only things that matters. Okay, so for distributions, the shape, the center, the spread, and the outliers are things you need to address. Some of you talked just about the center and not the shape, and you talked all about the quartiles, which is great, but you didn't actually talk about which one was more spread out and which one was less spread out. So we need to focus our descriptions. When we describe a scatter plot, remember, the scatter plots are for quantitative variables only. We can't put a scatter plot together with categorical variables. We talk about the direction. Is it positive, increasing from left to right? Is it negative, decreasing from left to right? Remember that we read a graph like we read a line. Positive. Actually, I don't want to draw a line like this. I want to kind of draw points. Okay. Is it negative? Okay, so we have positive and negative. So direction. Form. Is it generally a straight line, or is it curved in some way? Not linear, not straight. Okay, so you have points that are basically a straight line, or you could have curves. Right? Is it curved? Yes.
So for your sketch with the positive and negative ones, are those positive ones like in quadrant 1 and the negative in like quadrant 4?
It could be. Most of the time, scatter plots in stats are going to be all positives, right? Because we're talking about height and weight, shoe size, length. We're talking about a lot of variables that are positive. So sometimes it'll be negative if it's like the difference between some things, but the majority of our scatter plots are going to end up in quadrant 1. Scatter. How scattered are they? Do they follow a single stream? Like here we have tightly scattered. Both of these are tightly scattered where they're pretty close together. Or here these are moderately scattered. They're more spread out, right? Or are they really spread out, loosely scattered? Okay, and if there's no pattern, we call it random scatter. And are there outliers? Do there seem to be points that are far away from the rest of the data? So we're talking about direction, form, scatter, and outlier. And the acronym someone came up with one year was, oops, that's not a pen. SOFD. FODS, DOF, I don't know. It's not a very good acronym. Not as easy as SOX. But direction, form, scatter, outliers. Direction, form, scatter, outliers is what I'm going to say over and over and over again. Make sure you talk about direction, form, scatter, and outliers when you're describing a scatter plot. Okay. Okay, so let's imagine these scatter plots and describe what they might look like. The first one is drug dose and pain relief. Which of these seems to be the explanatory variable, the X variable? What? Drug dose? Right. If you are in pain, how much medicine you are given determines how much relief you get from the pain. Right? And not pain level, right? Pain level would be going down as drug dose went up, but this is pain relief, how much relief you are getting from it. So relief is increasing as the drug dose increases. So we have okay, so first of all, we're looking at which one goes on the X and Y axis. And then as we increase the dosage, the pain relief goes up, right? And do you think this is going to be really, really tightly scattered or probably pretty spread out depending on the person? It's going to be pretty spread out, right? And at some point it might level off. It might level off because there's just, the pain's gone, right? It could level off because there's a tolerance. It's going to be scattered because everybody has a different reaction to medicines. So our next one. Calories consumed in weight loss. What's our explanatory variable?
Calories consumed your action weight loss is line.
Again, it's weight loss, not weight, right? So how is this going to react? As you increase calories, what's going to happen to your weight loss? It decreases, right? So the more calories you consume, the less weight you end up losing. So, and is that pretty scattered, or you think it's super tight? Is it a perfectly straight line? No. No. We might have two even different graphs. You talk about boys and girls, the most unfair thing in the world, right? They can eat whatever they want and not gain a pound. We look at a cookie and we gain weight. So the weight loss is going to be good, the higher. And now don't always assume that your graph starts at 0, 0. Your graph might start at 1,200 calories, right? We don't need every scatter plot to start at 0, 0. We need it to be where the data is, okay? So, again, scattered. Might there be some outliers? Just adding those in for fun. Yeah, sure, there could be outliers, right? Because there's more variables, there's more things that affect your weight loss than just how many calories you eat, right? Exercise, genetics, sometimes the type of calories you eat, depends on who you listen to. Okay, hours of sleep and score on a test. Could score on a test cause you to not sleep well? Maybe. You tell me. How did it go last night after you got your test scores? Did you sleep well or not so well? Sleep would probably be your X. We're talking about sleep before the test, right? And test score. What do you think that looks like?
The more you sleep, the better test score you get.
Okay, but what if you sleep so much that you don't study?
Oh.
Could it actually start down here and peak at a certain point, like a maximum or an optimal amount of sleep? And then could it then go down if you get no sleep because you're playing video games? Right? Is it possible that it could look something like that? I had a roommate, well, a hallmate in college. She lived in the dorms. He would stay up till 3, 4 in the morning for our 8 o'clock biology class every time there was a test and study. And he was like studying. He wasn't playing video games. He was studying until 4 in the morning. I went to bed at 10 o'clock every night. Yes, that's me. Early to bed. And was like, there's no more studying I can do at this point. If I know it, I know it. If I don't, I don't. I always did better than him, right? He was always so sleep deprived, he could barely think. Time to run a mile. Oh wait, I forgot shoe size and GPA. This one's always fun. Shoe size. Can your GPA determine your shoe size? No. Your feet are not going to grow because your GPA goes up, right? Now, we're really talking about like teenagers. You don't have a GPA in elementary school, right? So we can't do that. But do you think people with bigger feet are smarter?
No.
I mean, I wear a size 10. I have big feet.
Size 10.
No, shoe size has no relationship to your GPA, right? There's no way how big your feet are affects how smart you are, how well you do in school. So this graph is going to look like a big random cloud of points. Some people with small feet have good GPAs. Some with small feet have bad GPAs. Some with big feet have good GPAs. Some with big feet have bad GPAs. There's no association or correlation between these two variables. Okay? How about 5 is timed for a mile and age? Which one is our Y? Or X, sorry. Age. What do you think? Positive, negative?
It's going to be a rainbow.
Rainbow. Upside down rainbow? Or
I think.
down or
If
up?
you're a baby.
You're probably not running a very
not
fast
running a
mile.
very fast mile.
Right.
And when you have peak performance.
So there's an optimal age for the mile time. Are there lots of variations here? Yes. There are 60-year-olds that could probably run a mile faster than me.
There's 60-year-olds that can probably run a mile faster. I bet I'll outswim them now.
So we're looking at more of like a big scattered U, right? Because if you're really young, you're probably not that fast. And then you reach that optimal age and you hit your peak performance. Like, there's a reason most Olympic runners are around the same age, right? That's their peak performance. You don't see a lot of 60-year-olds in the Olympics, right? So as you get older, you slow down a little bit, and your mile time is probably going to get higher and higher. Okay, yes, of course, there's some exceptions to the rules, which is why it's so scattered. Because there's other variables than just your age that determines how fast you can run a mile, right? And those variables are called lurking variables. You can look at two variables on a scatter plot, but there's other things that affect it. There's other things that affect those two variables. There's lots of other things that affect GPA rather than shoe size. There's lots of things that affect your test score, not just sleep. Does sleep affect it? Sure. Hours of studying, right? That's going to have a bigger impact maybe, right? So age and mile time, there's a lot of other factors there, okay? And how about the age of a car and cost of repairs? Age of the car.
Causes the repair cost to increase.
So the brand new cars generally have low repair costs, especially because they're under warranty. Then what happens as they get older?
Less parts for them.
They get more, they start breaking more, right? And it's just going to keep going up. Yeah? Might it turn and go back down? Might it level off? Might it go back up? All right, the more vintage the car gets, the more expensive it becomes to repair. Right? It might dip back down like a brand new car if it's under warranty. And if it's just out of warranty, might cost you more than a car that's 15 years old. Okay, but it's definitely not a straight line. And it's not a single stream. It's very spread out. And there's lots of scatter because there's lots of different variation in what causes the repair to cost so much.
What would be something that is just a straight stream?
So there is like scientific relationships. I'm trying to think. When we are using correlation, we have to make sure the variables are quantitative. We have to make sure the data is straight enough. It doesn't have to be a perfectly straight line, but in general, a linear form. And there can't be outliers because outliers distort correlation. Outliers can make a small correlation look really large, and it can make a large correlation look really small. When there's outliers, it's smart to report the correlation with and without the outlier included. So sometimes you can say, there's this really crazy outlier. I think I'm going to see what the correlation is without that outlier. And if it changes drastically, it's important to mention that and write that down. And you say that in the last 7 years, this is actually very old data. But let's say in the last 7 years, the number of students taking AP Stats has risen from 5,000 to 60,000. And the murder rate has dropped considerably. This has a strong negative association, but it doesn't really have any correlation, right? You can take two totally unrelated quantitative variables and put them on a scatter plot and find a correlation. That doesn't mean there's an actual correlation between them, because you shouldn't say if everybody took AP Stats, there would be no murders. Okay? That's an absurd statement, right? So you have to be careful when you're putting two quantitative data together, and it doesn't make sense to even talk about there being a relationship and a correlation between these two things. Okay, so we need to turn on our diagnostics. There's a way we're going to get our linear regression equation and our correlation, but if you don't have the diagnostics turned on, it's not going to work. So I need you to hit the second button. Second. And then above the 0, it says catalog. Okay, so you're in here, second catalog. And we're going to use the alpha button to go to the D's. Or you can just scroll all the way down. And you need to find diagnostics on. Okay? If you don't have diagnostics turned on, it's not going to give you your correlation. And that's one of the things we're going to be finding this chapter. So now hit enter, and then enter, and now they're on. Okay? Now, I want you to go to your second list. And I want you to see if you have any lists in here labeled MHT, MWT. Do you have any lists in there? Male height, male weight, female height, female weight.
I have MHT, MWT, SHT, and MWT.
Okay, so you already have the data entered in. I do not have the data entered in. Okay. Now, go to Stat, Edit, and highlight L3. Highlight L anything. And scroll all the way over until you see a blank list. Highlight the lists, just list 1, list 2, whatever, the list number, and scroll over. If you're in the actual data, it won't let you scroll all the way over. So we're going to scroll up. We're going to scroll over to the empty, and we're going to type in MHT for male height. So my alpha is the green button. MHT. Okay. So I'm creating a list and naming it so that it's not taking up my lists 1 through 6 while you're working on homework, and we can recall it for a bunch of things. If you already have it, you don't need to do this.
How did you get the letters?
The letters, use the green alpha button. And if you look above the numbers, you'll see a green letter.
Oh.
Yes, Faith.
I already had it in mind, but it's not showing up like right here.
Right, that's okay. If you actually type MHT at the top, it'll fill it with the numbers. And then scroll over again. And you're going to type in MWT. So we're just creating these lists in the calculator, and then I'll give you time to enter in the data. It didn't? Did you hit enter and then down, maybe? I'll have to look and see. And then we're going to do the third one. I'm going to do, you could do WHT, women height, or FHT, female height. And
Row, it's not.
so you should have 4 lists that are labeled here.